Maybe you can start now. Yeah.
Um, all right. So our speaker today is Derek Koo from A Star. He's gonna talk about error correction, contextuality of error correction. And Derek, I know like probably you wanna try and share your slides, see if it's working.
Oh yeah, let me try do that. Okay. Um,
Okay, I can't see it now. I know probably you wanna like put it in like full screen mode or something. Yes, looks good. Um,
should I start? Oh,
I I don't know, like probably let's wait for like uh 4 past 4. I don't know, like just one more minute to see if I okay, so
yeah.
it's 4 past 4 now. Um yeah, I guess just let's just start now. Okay, I'm just gonna reintroduce you then. So our speaker today is Derek Koo, and he's a scientist in a I Square R in A Star Singapore, and he's gonna talk about contextuality of error correcting codes. So yeah, take it away, Derek.
Hi. Yes. So today I'll be talking about this recent paper of mine and Kishore and Andrews. So we were looking at how to define the contextuality of quantum error correcting codes. And so yeah, so a brief outline of what I'm going to be covering today I will first be talking about the shift theoretic framework for contextuality. So how we define contextuality in the shift theoretic sense. And then we talk about partial groups and partial closure. And then I'll give a brief overview or kind of like a recap of what stabilizer codes and subsystem codes are and define what contextuality means in that context. And then we can discuss some of the main results for paper and then finally the discussion, a summary of what we have. So what is contextuality? So I imagine many of you might know what the Penrose staircase is. So imagine you want to figure out what the heights of the different parts of the Penrose staircase is, but you only have like a small little telescope that you could look through, and you see that over here, the staircase goes kind of higher and higher in the counterclockwise direction. And then again in the counterclockwise direction, it goes higher and again and again. So then the question is what are the heights of all the parts of this staircase? We see that in the global view, actually, this is not really consistent at all, right? Because it just keeps going up forever. And so this is an example of something which looks locally consistent, but it's actually globally inconsistent. Because it's locally consistent because you could kind of assign heights to the staircase in like local areas, but you cannot assign like a global consistent. You cannot have like a global consistent assignment of heights. So this is essentially this what we are this is actually what happens in this shift theoretic definition. So first we define what a quantum measurement scenario is. So X would be the finite set of observables on some Hilbert space. So this you could think of as like the Pauli operators if you want, but it's just any finite set of observables, a non-empty of course. And M will be the set of maximally commuting subsets. So you look at all the subsets of X and then you take the maximally commuting ones. And O would be the set of all measurement outcomes for each observable. So in the case of Pauli operators, it might be just plus or minus 1. And the event shift, we could define, oh, this should be like a regular X. The event shift we could define on X by setting for any subset of X, the event shift would be all possible outcomes on all the points in the subset U. So if you were like say two different observables, then the E of U would be all 2 to the 2 possible outcomes if O were say a set of size 2. And restriction maps would be for this sheaf would be given by, so if you take a section S in this, so these are the sections of X. So if you take a section over U, and then the restriction map will be just taking the restriction of all the outcomes. So you kind of throw away all the outcomes there, throw away all the elements that are not in U prime, and then you are left with the elements in U. So that is the restriction map. Okay. Is this definition clear? Yes, no, any questions?
Yeah.
Okay, so now we can talk about the distribution pre-sheaf on X. So if we have a semi-ring R, then the pre-sheaf would be, this distribution pre-sheaf would be for any subset U of X, we can consider all the R distributions on O to the U. So remember, O to the U is basically all possible outcomes that could be obtained by observing the observables in U. And so this distribution pre-sheaf is just giving a set of kind of probability distributions, if you will, over all the possible outcomes. So when R is equal to the positive real, the non-negative real numbers, then we do get the probability distributions. And the restriction maps in this case for this pre-sheaf would simply be kind of, this is really just marginalizing the distribution. So if you have a distribution over a bigger set, and then to restrict that distribution to a smaller set, we are just taking the marginal distribution. And finally, what we mean by an empirical model. So if we have a semi-ring R, again, an R value empirical model would just be looking at all the maximal contexts. So for every maximal context, we could assign a R distribution to it. And the only condition that we need is that the restriction on the overlaps would coincide. So if we have two distributions, if we have two contexts which overlap in some set C intersect C prime, then their overlap must have the same marginal distribution. So this is
I have
basically
a question.
Yes.
So does there need to be some kind of, say, sigma algebra structure on on X, like for there to be consistency in assigning these? So it's like R valued measures somehow, right?
Yeah, so over in this case, we are just taking X to be like a finite set. So so X would just be like a finite set, and this sheaf we are thinking of X as like a discrete topology, the discrete topology on X. And so I guess it's really the counting measure, like basically to each point in X, we are assigning a value in R, and the sum of all the values in R must add up to 1.
Okay, thank you.
Well, yeah, so yeah, maybe I should revise that. To each possible outcome. So it's not to each element in X, it's to each possible outcome. So if you have, say, 2 elements, then there are 4 possible outcomes, right? If let's say your outcomes are 0 and 1, then you could consider 0, 0, 0, 1, 1, 0, and 1, 1. So you have 4 possible kind of values that you give that should add up to 1. Any other questions? So now we could talk about the probabilistic empirical model. And so this is really a sub pre-sheaf of the event sheaf E. So the event shift is all the possible outcomes. So to each section, you assign all the possible outcomes. And so a probabilistic empirical model would be a sub pre-sheaf of that. So basically, for every subset of X, you assign a subset of the possible outcomes, which you say are kind of the possible ones in your model. So the conditions that we needed to satisfy is that for every maximal context, you must have at least one possible outcome. So essentially, it means that for any measurement that you make, you must have at least one possible outcome that you can get from the measurement. And this says that based when you have two subsets, when you have two sets U contained in U prime, in both of them being in the same maximal context, the restriction map is surjective. This is effectively the no signaling condition, which means that if something is possible in a smaller set, it must have been possible. It must have come from something in a larger, like in a measurement of a larger set. And so this is no signaling. And finally, there's this condition where if we are able to consistently assign, if we are able to consistently choose sections from everything in the maximal, from all the maximal contexts, then we can glue them together into a global section. So it must be a consistent choice that agree on the overlap. So for example, in the case of the Penrose staircase, you would not be able to do this because in every case, the thing to the left, so in the Penrose staircase, there is no way to assign consistently all the heights such that they all agree on the overlaps. So it's very important that here, only if your family agrees on the overlap, then you can get a global section. So these are the three kind of conditions that we need for a to be a probabilistic empirical model. And yeah, so this definition of a shift theoretic framework for contextuality actually came from an earlier paper by Abramsky and a couple others. Basically, they kind of showed that they came up with this definition and they kind of distilled these three as like the kind of key parts of the definition that we need. And so finally, if we have an R value empirical model, we can also obtain a possibilistic model by just restricting by just choosing the sections to be such that using this definition, basically anything which is supported on the model would be considered possible, and anything which is not would be considered impossible.
Okay,
Any
so here
questions?
I have another question.
Yeah.
So the possibilistic model doesn't really care about the measure that you assign, except in it being zero or non-zero, right?
Yes. Yes.
So in that sense, is it true? So can there be weird cases where there is a consistent possibilistic model, but the measure doesn't restrict in the natural way that we think of, where you like, if you take a measure on a restricted uh, set of events, then it will just be the uh, the restricted measure normalized by the measure of that subset or something, where it can be something else.
Yeah. I don't think so. So yeah,
Okay.
I think so. In fact, anything which is, yeah, I'll kind of get to that slightly later, a few slides later. But yeah, the answer is kind of no. So anything which is basically, um, well, so are you asking if something which is possible is definitely, I mean, it depends on which direction you're asking.
It's more like, okay, let's say I have a possibilistic model. Can I have some case where the possibilistic consistency holds, but when I restrict on the level of the R-valued empirical model, then the way that the measure behaves is not as we naturally have, which is just like in our usual sense of probability measures. If I take an existing measure and then I take only a condition, it's like a conditioned measure, right? I take on a restricted,
Yes.
then it has a certain sense of linearity normalized by the probability of that condition and so on. But can that be violated whilst upholding the possibilistic condition?
Yeah, I believe the answer is no. I believe if
Okay.
you're possible, there definitely is an R value model.
Okay. Okay.
Yeah.
Okay. Thanks.
I mean, like, let's say at the level of empirical model, like nothing should break, like it should be a valid empirical model. But then what you can have different, like, hierarchy of contextuality. And for example, like the highest hierarchy that you have is a strong contextuality. So for example, you could have possibilistic, like contextuality, but it may not be strongly contextual. Like this kind of scenario can happen, but always it will be a valid empirical model. I mean, like, I think
Okay. Thank you.
like, yeah, that
Yep.
helps. Yeah.
Yeah, so let me move on. Well, the kind of the general idea is that the kind of a general idea of the proof is to see why that is true, I believe would be if you set R to be the if you choose R to be, say, 0, 1, where 0 represents not possible and 1 represents possible, and then the operation is just addition is or addition is or and multiplication is and, I guess. Maybe not. So, well, you want 0 plus 1 to be, you want 0 plus 0 to be 0 and anything else to be 1. And then you should be able to get, and then you should be able to, like, uh, use that idea to prove something like this. I think it's maybe coming up, at least in the probability case, you could come up with like a homomorphism to that. But yeah, I would need to think about like how to prove this a little bit.
So yeah, please. I didn't mean to like
Yeah, no
derail.
problem.
Yeah.
Yeah.
Please carry on. Yeah.
Anyway, so we could talk about the empirical model defined by a quantum state. So if we have a quantum state rule, then we could talk about the empirical model that we get when it's from this quantum state rule, which is basically what the probability distribution of the measurable outcomes that we get from measuring each of the contexts, each of the maximal contexts. And the possibilistic one is just the possibilistic model associated to this. And so what do we mean by contextual? We say a model is contextual if there is no global distribution which restricts to each of the marginal distributions that we have in the model. And strong contextuality means that basically means that there is no global section for the possibilistic empirical model. And it is a fact that a strongly contextual model is in fact also contextual. So I think this is related to the question they asked just now. Any questions? No. Okay, so Here's
I mean, sorry, can you just stay on this slide for a bit and because I think it's very terse. There is a lot to absorb.
yes. So contextuality, yeah. So I'm gonna give kind of two examples over the next few slides. But basically, contextuality means that if you have an empirical model, which means a collection of distributions over each of the contexts, you cannot find a joint distribution that restricts to each of these marginal distributions. And a possibilistic one, a strongly contextual possibilistic model is given a sub presheaf of the event sheaf. So basically, for every context you if for every subset of X, you kind of declare certain things to be possible and certain things to not be possible, there is no way for us to consistently choose a set of there's no way there's no way for us to choose um a kind of a global section. So there's no way for us to choose like a section which agrees with everything. So strong contextuality has to do with possibility, and contextuality has to do with the probability distributions.
So may I know how to understand it in terms of that equation where you say S of X has to be the empty set?
Yeah, so S of X is so here so S is a sub presheaf of E, right? So E is the event sheaf where basically S of every section is just a subset of the possible outcomes. And it just has to satisfy all of these conditions. So these are so basically for every context, you must have at least one possible measurement outcome, and then it has to restrict well. So there's kind of like a no signaling condition. And the last one just tells you that if you could consistently assign an outcome to every context that agrees on the overlap, then you get a consistent outcome. So the the condition that the global section is empty, the set of global sections is empty is the same as saying that there's no way for us to consistently choose context in order. There's no way for us to consistently choose a family of sections. So basically none of this, this S of C do not kind of agree consistently across all the C's. So we'll see an example later, and hopefully that should clarify things. So here's something that's contextual. So given a quantum state, so if you do the calculations on this quantum state, you'll see that if we do, so x1 over here means x tensor I. So and x2 means I tensor x. So measuring x on the second qubit and measuring x on the first qubit. So if we do a measurement on this quantum state, we should get this table of probability distributions, where this +1 and -1s are the eigenvalues corresponding to the operators. And so asking whether it's contextual or not is the same as asking, is there a joint distribution of all of these x1, x2, z1, and z2 that give rise to this marginal distribution over here? And it turns out that the answer is no, because if we look at this table over here, the probability that if there is a joint distribution, the probability that these two eigenvalues are different is 0.8. But in order for these two eigenvalues to be different, either Z1 has to be distinct from X2, or X2 has to be distinct from X1, or X1 has to be distinct from X2, Z2, right? Because if all of them are the same, then these two would have to be the same. But this probability is bounded above by the sum of all the probabilities. And if you look at the table, these are the probabilities that they are different. So if we sum these things up, you should get only 0.4. So there is no such joint distribution that gives rise to this. So this model is contextual. Questions? All right, so now we could ask if this is non-context, if this is strongly contextual. But here we see that for every measurement outcome, for every set console, each of these rows represent a context. And for each of these contexts, all of the possible outcomes are possible. So actually, there is not strongly contextual because we could just choose a global assignment where all these things are equal to 1. Then that is a plausible that is a plausible kind of global assignment. This is a possible global section that restricts to these local sections. So the ticks across the table would be this. So these 4 would be the possible local sections corresponding to this context. These 4 would be the possible local sections corresponding to this. And this will be for this, and this will be for this. And this thing corresponds to these 4 local sections. So these 4 local sections agree on their overlap. So for example, in this 2, this and this agree that x1 is equal to 1. And this agree that this and this agree that z1 is equal to 1, and so on.
Yeah, so Varun, I mean, if you can try to think of in terms of probabilities, like let's say no ship. I mean, it's basically what we are saying, that there is no joint probability distribution that is compatible with any marginal probability distribution over the context. So that's like strongly contextual. On the other hand, when we talk about the other case scenario, there, what we are saying, that given a marginal distribution, there is no joint probability distribution that is consistent with it. So in one case, you are saying given a joint probability, given a marginal distribution. In the other case, you are saying that there is no joint probability distribution that is compatible with any combination of local probability distributions. I mean, like marginal probability distributions.
Got it. Yeah.
Yeah.
Thanks.
So an example of something which is strongly contextual would be the Mermin-Perez square. So if we look at these 9 Pauli operators, each row and each column is a maximal set of commuting operators. So each row would commute and each column would commute, but they would not jointly commute with anything else. And
Derek, you're muted.
okay, hi, can you hear me now?
Yep.
Sorry. Yeah, so these are each row and each column represents a maximal set of commuting operators. And the possible measurement outcomes would be, say, for this row, it would be, so for say this row could be any of these 8 possibilities. And we could ask if there is a consistent way to assign values to each of them. But we see that when we multiply these operators together, they give us the identity. So we must measure the product of these outcomes must be +1. So they have to be one of these things. And each of these would give +1, we would give the identity basically. So each of these would give a +1 as the product of the measurement outcomes, except this one would give a -1. And the question is there a consistent way to assign values to each of them? And the answer is no, because if there were a consistent way to assign measurement outcomes to each context, then the product would have to be, the product of all 9 would have to be both +1 and -1, which, because +1, but if you look at the rows, -1 if you look at the columns. So this is a contradiction. And so therefore there is no consistent way to choose anything. So so this is an example where there is no global section. So there is local section because for every context, the local sections are these things. Well, so for, let's say for the first context, the local sections are this 4. And for this last column, the local sections are these, the last 4, right? But there's no global section. So you can't, there's no way for us to glue together to get like a coherent global section. Is this okay? Okay, so now let's move on to partial groups. So this is the full definition of what it means to be a partial group, but it's well, so simply put, it's basically a non-empty set P, and then you could look at the word. So P star would be all the possible words that you could form using the letters in P. And so it's a set of, so the partial group is this set P, but you also have the data of which words are allowed. So you can choose which set of things you could, in some sense, multiply together. So there is a product operation. So you could specify a set that you are allowed to take products of, and then you can also take the inversion operation on this set P. So this is basic, and these are basically the kind of technical conditions that that make this definition work. But what I described is basically what it means to be a partial group. So maybe an example would kind of clarify this definition. So in the case of a poly group, so you could set the set P to be the poly n group. So basically all possible poly operators along with the phase. And D, the set of allowed words, would be any possible concatenation of pairwise commuting operators. So you only allow products of things which commute with each other. And so the product will be the regular group operation of product, and the inverse will be the regular inversion operator. And in this way, we get a partial group where the products are only, where we restrict products to only being for the ones that commute with each other. So in some sense, this kind of corresponds more with the definition, with the idea that you could measure commuting operators simultaneously, but you cannot do simultaneous measurements of non-commuting operators. Is this clear? Okay. And so what is the partial closure of a group? So the partial closure of a group is, well, let's talk about partial subgroup. A partial subgroup is basically a subset of your partial group that's closed under inversion and products. So for example, if we look at a poly group in the previous slide, a partial subgroup of it would be basically the ones with a phase of plus or minus 1. Right? So because if you take the product of any two things with any two of those polys with plus or minus 1 phase, then the product also has a plus or minus 1 phase. And the same with inversion. So it is a poly subgroup. So it's very similar to a subgroup of a group. Here it's just, we call it a partial subgroup. And then we could talk about a partial subgroup generated by a subset of the partial group, or also what we call a partial closure. So for example, if we have these 4 operators in Pn, so these are the 4 operators in, so Pn, as we recall, is the n polys with a real phase. So we let Gn, we define it to be all the possible n poly operators with any phase +1 or ±1 or ±I. Pn, we take it to be a n cubic Pauli operator with the phase ±1. So if we look at the partial closure of these four operators, how do we figure out what a partial closure is? So the partial closure basically says that it has to be closed under products and inverse, kind of taking inverses. So all of these are self-inverse, so the condition of inverse is kind of vacuous, but in order to be closed under products, you see that you must have the identity operator, because you take the product of any of these operators with itself and you would get I. But if you take the product of x1 and x2, you get x1, x2. You take these two, the product of these, you get that. And the product of these, you get this. And the product of these, you get this. So the partial closure must contain all of these in order for it to be closed under products. But then we can take the products, we can take products again. And we see that if we take the product of these two operators, which commute, x1, z2, and z1, x2, they commute, and if you take the product, we get y1, y2. And if you take the product of these two operators, x1, x2, and z1, z2, we get y1, y2. Oh, we get minus y1, y2. So we get both plus and minus y1, y2. And now we can take products again. And you would see that you get more operators after you take products. And finally, when you take products, again, say from the minus I with these four operators, you get these. And one would realize that if you try to take products of any two commuting operators in this, you would remain in this set. So it turns out that these are all the elements in the partial closure of these four operators. Is this okay? So why are these four operators? Why is this partial closure strongly contextual? So we did see a proof using the just now, as we talked about with the Paris-Mermin square. But another way to see that it's strongly contextual is to use determining trees. So each of these trees has the property that the parent is the product of its children, and all the children of each kind of subtree. Well, all the children of a parent would commute. So these two commute, 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 and these two commute. And their product is the parent. And we see that both of these trees have the same leaves, but the kind of root of these trees are y1, y2, and minus y1, y2. So whichever values of plus or minus 1 we assign to these leaves, we have the same leaves over here. So we should expect the products to be the same, but clearly they should differ by a sign of -1. And so we get a contradiction. So this is another way we establish strong contextuality. And this was a way discovered by Kirby and Love. So we call it KL contextuality. Any questions? No. All right. So now a quick review of stabilizer codes and subsystem codes. A stabilizer code is basically defined by an abelian subgroup of the poly n group Gn. And as would have, like, this abelian subgroup would have to have basically real phasing. And the code space is basically the code stabilized by the subgroup, but it's not particularly important in our case. And the check measurements will be a minimal set of generators of this abelian subgroup. And the subsystem code is defined not just by this abelian stabilizer group, but you also have a gauge group, whose center is I times the identity and the stabilizer group. So the subsystem code, the check measurements in this subsystem code is a minimal set of generators of Pn, such that together with I times I, we generate the entire gauge group. And so the important property that we need to use of subsystem codes is that we can construct n pairs of virtual kind of poly x and z operators. So we call these xj prime and zj prime, and they should satisfy the usual poly-op relations, which is that basically xj prime would anti-commute with zj prime if the two j's are the same, but xj prime and zk prime would commute, and so would all the x's and all the z's. And the check measurements in this kind of code, so this is basically kind of rewriting the code in a different basis. And in this new basis, the check measurements would just be, the stabilizer group would just be the group generated by the z operators up to some point in zs prime. And the check measurements will be all of these a set of independent generators of this stabilizer group, along with x and z's of another g more qubits. So all of these would form the check measurements. And these are kind of the measurements for the gauge qubits. So over here, we say that they are G gauge qubits. Any questions? Right. So what do we mean by subsystem codes being contextual or not? We can just basically look at the set of check measurements of the error correcting code. And we say it is contextual if that set of check measurements is contextual, and we say the code is strongly contextual if the check measurements form a strongly contextual model. So basically, the idea is that we are looking at the check measurements of each of the subsystem codes, and as long as it is contextual for some quantum state, we say that it's contextual, and as long as it's strongly contextual for some quantum state, we say that it is strongly contextual.
So just to clarify, if I connect back to what was said previously, so here when you say the empirical model defined by some quantum state being contextual, it means that there exists some quantum state, and there exists some
Yes. This means there exists a quantum state for which the empirical model, because the empirical model is defined by measuring the check measurements on some quantum state. So yes, it's
okay. But is there another existential thing there in the first point? Because what Kishore mentioned earlier about contextual versus strongly contextual. Contextual was about there exists a set of let me recall marginal distributions over sub sets of the events that don't come from that are not marginals of any mother distribution.
yes.
Strongly contextual means that for any set of distributions, this holds, right? So in that sense, can you? So if you give me a quantum state, then where does the distributions?
Yeah, no. So if given a quantum state, you can measure the quantum state on each context. So each maximal set of commuting operators, we can use those and measure the quantum state, and that should give you one distribution. And you can do this for all the contexts. So you get multiple marginal distributions that you are hoping to glue together to form a joint distribution. So it is contextual if you cannot glue them into a joint distribution. And strongly contextual means instead of viewing the things as probabilities, you just view them as possibilities. So as long as on that particular quantum state, you do your measurements from the context, as long as an outcome is deemed possible, you just say that it is one of the possible outcomes. And then you do this for all the possible contexts, and then you see if there's any consistent way to assign possibilities, not probabilities,
I mean,
of
Derek,
these.
I think maybe for future, I think it might be nice, like to put the slides like picture for Hardy versus a PR box. So
I see.
then one can very easily see, right? I mean, what this corresponds to, like,
Yes, yes,
the two cases, yeah. Like,
yes, yes.
yeah, then easier to visualize basically.
Yeah, yeah.
Yeah.
Okay, so strongly contextual is like Hardy kind of thing where,
Strongly it's like PR box, yeah.
okay, okay.
It's like
Mhm.
the maximum you can get, yeah.
Yeah.
Okay.
Yeah. Like, yeah. And basically what we show, I think Derek will show that, like under partial closure, all of them collapse and they become same.
Yep.
Yeah.
Yes. So yeah, and we can define the corresponding things for partial closures as well. And so when is a subsystem code contextual? We can look at, so this is a theorem we proved, which is that if we have a set of check measurements for a G gauge qubit subsystem code and a set of maximal commuting subsets of C bar. So C bar is the partial closure of C. And then we have some empirical model. Then this empirical model must be non-contextual if there's only 2 gauge qubits, or if there's less than 2 gauge qubits, so either 1 or 0. And it is strongly contextual if there's at least 2 gauge qubits. So here we are talking at the level of the model itself on an arbitrary quantum state. So it turns out that this result doesn't depend on which quantum state you started off with. And therefore a corollary would be that it is strongly contextual if there are at least 2 gauge qubits, and the code is non-contextual if there's less than 2 gauge qubits, because here we remove the dependence on the quantum state. So here are some examples. A stabilizer code is basically a subsystem code with 0 gauge qubits, so it is non-contextual. The Bacon-Shaw code has 4 gauge qubits, so it is strongly contextual. And if we look at the Hastings-Haar code as a subsystem code, it is strongly contextual also, because there are at least 2 gauge qubits. And so now I'll kind of give like a rough sketch of where this G is greater than or equal to 2 condition comes about. To see this, we kind of have to introduce a notion of a compatibility graph of a set of observables. So this compatibility graph basically gives an edge if 2 operators commute. So you have your vertices would be all the operators, and then you draw an edge if they commute. So we say a graph has the Kirby-Love property because they introduce basically this property in their paper. If you have four vertices, A, B, C, and D, such that A and B and A and C have an edge, A, D, and B, C do not have an edge, and the other two you could choose whether or not they have edges or not. And so one of the key lemmas that we showed is that if G is greater than or equal to 2, then the compatibility graph would have the Kirby-Love property. And the proof is basically rather straightforward. If there are no gauge qubits, then all the operators commute, right? Because you don't have any anti-commuting X and X stuff in this. So all the operators commute, and so you do get the you do not have the Kirby-Love property, because to get a Kirby-Love property, you need something. You need this kind of compatibility diagram. If G is equal to 1, you have one pair of anti-commuting operators, so you have up to this point. And we see that there is no way for us to get this Kirby-Love diagram, because you need two pairs AD and BC to be anti-commuting. But over here, you see that there's only one pair of anti-commuting operators, so you do not get such a subgraph. And if G is greater than or equal to 2, you do get such a subgraph, which is basically given by this diagram. And so this is kind of basically where the G is greater than or equal to 2 condition comes from. And with that lemma, it suffices to show that these three conditions are equivalent, which is given any set X, any subset X of Pn, and M bar defined the same way as sub rho defined the same way. If your compatibility graph has the Kirby-Love property, then you are strongly contextual and you are contextual, and all of these three properties are basically the same. And the kind of the high level idea of this proof is to show that these conditions are all the same, even if we don't take partial closure. So there are these other definitions of contextuality, which I won't go into, but the idea is that all of these are different definitions of contextuality, and we could show that all of these are we have this chain of implications, even if we don't take partial closure. And most of these have been kind of proven in our previous work, or similar proofs exist before. But so this is the kind of more interesting part of the proof, where we prove that being contextual means that you must have this Kirby-Love graph property. And if we take partial closure, we can in fact show that these two properties are the same. So it means that if we take partial closure, all of these properties end up being the same. So this is kind of like the high level proof of our main theorem. And to kind of give a sketch of how we proved contextuality implies the Kirby-Love property, here is a proof that a strongly contextual model has this Kirby-Love property. So first, we prove that if a graph is not Kirby-Love, so it doesn't have any of these, this is not quite right, but yeah, this diagrams are not quite right. So if it doesn't have these any of these forbidden subgraphs, then the maximal clicks must look like that. After you remove the universal vertices, the maximal clicks must look like this. And so if your graph looks like this, where each circle is a maximal click, and each of these connections means every vertex in this context is every vertex in this circle is connected to every vertex over here. And the kind of rough idea of a proof is that first you choose a set of possible outcomes from U, and then you kind of extend it to each context. And after you extend it to all the contexts, the condition on the sheaves would tell you that there is a way for you to glue them together to form a global section, because any two contexts would overlap only in U. So as long as you start by choosing U and then extend it to all the different contexts, you would be able to choose a global section that for like the entire graph. And for contextuality, we kind of begin in the same way. We show that there is such a structure if it's not Kirby-Love. And then the question is, given marginal distributions on, say, U union C0, U union C1, and so on, is there a kind of joint distribution across all of them, and we show that basically you are able to define such a joint distribution, but I would not kind of go through the proof right now. And so finally, we can talk about the key findings in this paper, which is that we defined what contextuality means for subsystem codes and stabilizer codes. And then we talked about how to characterize contextuality in subsystem codes, in that if there are at least 2 gauge qubits, you are strongly contextual. And then we showed that different definitions of contextuality are actually the same if we take partial closure. And further things that we could explore would be, say, in dynamical codes, I mean, they are not technically subsystem codes. So it would be nice to come up with a more general way of kind of defining this contextuality that also applies to dynamical codes. And we could also ask what happens if we don't take the partial closure? Can we quantify the degree of all this contextuality of the codes? And also finally, if the the degree of contextuality would affect the kind of performance of these codes. Yeah, I think that's all. Questions? Feel free to ask.
All right. Yeah, so if anybody have any question, then you can just unmute your mic and ask away.
So I have like a few questions.
Mhm.
So I just wonder like how we can interpret the contextuality in the context of quantum alert collection. Like how does it help us understanding?
Yeah, that's a very good question. So this is actually something that we kind of want to understand further. I mean, we see that stabilizer codes are not actually contextual at all, and subsystem codes do give, say, the Bacon-Shaw code is contextual, is strongly contextual in a partial closure. So we could ask, and a property of the Bacon-Shaw code, for example, is that they have lower weights than, say, the Bacon-Shaw code compared to the Shaw code has lower weights. So it might be the case that a stable kind of contextual code might have better resource requirements, but I mean, it's again something that is worth exploring. Yeah, I don't have an answer at this point. So, but I agree, it's a very good and interesting question.
Thank you.
Questions?
So
Oh, also can you clarify what is cring mean in the graph? I forget about it.
What is what?
The cring,
Click?
yeah, what is that?
Oh yeah, it's like a complete graph. So it's like a graph where every vertex is connected to each other. So
Oh,
yeah, so each of U, C0, C1, C2, and up to Cm, they are all cliques. So they are complete graphs. So basically every vertex in U is connected to every vertex in U.
okay.
um okay, so if there's no further question, then yeah, I guess we can thank Derek again for the very interesting talk. And yeah, not sure if we're going to have a speaker for next week. Kishore,
No, I think next week is I think Yeah, like no talk. So we will meet in like 2 weeks, and next month we will have like I think 3 talks probably. Yeah, yeah.
Sounds
And
good.
okay, so I think we can pause the record, stop the recording maybe. Yeah. Yeah.
Thank